Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit. We are going to be talking about the Euclidean algorithm today, which is a method for finding the GCD of two numbers. As a quick reminder, the GCD, also known as the GCF, is the greatest common divisor or factor of two numbers A and B. So if you've heard the term factor before but don't know the term divisor, they just mean the same thing. So GCD and GCF are exactly the same. We're going to use the notation GCD of A and B today. Let's get started with the Euclidean algorithm then. We have two versions of it here on the slide, but they're pretty much equivalent to each other. So the first version says that if you're looking for the GCD of two numbers A and B, what you can do instead is look at their difference and the smaller of the numbers. So for example, if A is bigger than B and you need to find the GCD of A and B, you can instead look at the GCD of B and A minus B. So you can subtract off the smaller number from the bigger number and then work with the two smaller numbers there. Now, as we get into version 2 then, well, what happens if you keep subtracting off a number over and over, right? So if we have like 22 and 4, you could subtract 4 from 22 and you get 18. And then what if you do it again? You get 14 and 10 and 6, right? And 2. So this is kind of like division with remainder, which is all the second version says. If you want to find the GCD of A and B, this is equivalent to finding the GCD of B and R, where R is that remainder when you divide A by the number B. So, right, these steps can be repeated. We, of course, saw the subtraction repeated again. That kind of gives us version 2. But we'll see in a second in our example that you can do this quotient and remainder over and over until you get small numbers that make stuff easy to work with. Let's see everything in action here with an example then. So we want to find the greatest common divisor of 1200 and 252. Now there are a bunch of methods to do this, right? You can look at kind of just listing out the common factors. You can do some stuff with prime factorization and things like that. But let's practice here with our Euclidean algorithm for today. So if we look at this then, let's kind of do off to the side here our work. So if we have 1200, notice if we divide this by 252, it goes in 4 times. So this is 4 times 252. And you'll actually get a remainder of 192. So, right, you look at the quotient, it goes in 4 times, and now we can deal with the smaller number, 252, and the remainder. So this GCD here is equal to the GCD of the number 252 and 192. So now we have the smaller numbers to deal with here. Now this one's pretty easy. It only goes in once, right? So 252 is just following the pattern. It's 1 times 192, and our remainder then is 60. And right, you could stop at any time, right? So if you like some of these other methods for finding the GCD, you can of course kind of do this at any point if you say, okay, my number is small enough to work with here. But I just want to take this one more step to see here that it really kind of works pretty quickly to give us a nice answer. So now, right, these are numbers that we should all be a little bit more comfortable dealing with. 192 is 3 times 60 plus 12. So we can say this is equal to the GCD of 60 and the number 12. Now, why is this a nice place to stop here? Well, 60 is divisible by 12. So pretty clearly here, the greatest common divisor of these two numbers is 12. And what the key of the method is that this is actually the same as the original GCD, right? The Euclidean algorithm says, okay, we just kind of keep taking quotients and remainders and get the number smaller and smaller, and at the end, those GCDs are equivalent. So the GCD of 1200 and 252 is just 12. Thank you guys for watching today then. Check back each Thursday for new tidbits, and I hope to see you guys practicing on the ZIML site for more resources as well. Goodbye.